So today let's discuss a projectile motion problem with a tennis ball. The problem says the tennis ball is thrown from a second floor window towards the street. The window is 6 meters above the street. The angle it was thrown was 15 degrees above the horizontal at a speed of 20 meters per second. The questions are, how far horizontally will the ball hit? What is the time of flight? What is the magnitude and angle of the ball's final speed right before hitting the ground? So first, let's draw a diagram depicting the projectile. Okay, so let's see. Here we have 6 meters, and the projectile comes out at a 15-degree angle. This is an exaggeration of 15 degrees, so that I can draw the 15 degrees here. Draw this and a parabola, and the ball hit the street level. So let's use a ruler. Try to draw a better line, more straight line. Okay, here's a ruler. Alright, so at the end of that travel, we want to know this velocity, which is pointing downward. What is the angle here? And what is the magnitude? And the magnitude of the initial velocity is 20 meters per second. So first, let's have a list of parameters, as we always do with projectile motion problems. We'll have x0 equals, and we're free to choose the origin of our coordinate system. So let's choose the origin to start from here, the bottom left corner right here. So this is our origin, and our x-axis points to the right, our y-axis points upward, and here's a 0. So at the start of this motion, the horizontal position should be 0, and x, the final position, well, we don't know about that, so we'll just have a question mark here. And then let's move on to the y. Y initial, that is 6 meters, right? So y initial is 6, and y final, as the ball lands on the street level right here, the height is 0. Okay, so now we have, also we need initial velocity. So v initials x, which is v initial cosine initial angle, right? And we also have v initial y equals v initial sine initial angle. We know v initial is equal to 20, and we know the initial angle is 15 degrees. So we can calculate the initial x, which is 20 cosine 15 degrees, right? And this value is 19.3. And v initial y is 20 times sine 15 degrees. And this value is 5.18. Keeping 3 digits. Okay, so now we have all these. What are the equations? Well, the equations are the same, right, for projectile motion. There are these 3 equations. X as a function of time is equal to x0 plus v0 times t, and y is equal to y0 plus v0 times t minus 1/2 gt squared. So now you may have realized there's actually x and y differences, right? So the initial velocities are in components, right? So v initial x only affects the x motion, v initial y only affects the y motion, right? So vy is v initial y minus gt. So these are the 3 equations. Let's call them 1, 2, and 3. And the next step is to plug in these numbers that I listed above into the equations. So let's start with equation 1. Okay, so equation 1. unknown x, let's just use x, equals initial x is 0 plus initial velocity 19.3 times time. Okay, let's also put a time here. I think I missed that. What is the time t here? Right. So that's it. This is just 19.3 t. Two unknowns. We should move on to the next equation. There's no way we can solve this equation just by itself. So move on to the second equation. Y, landing on the ground, street level, starting at 6 meters, plus 5.18 t, minus half g is 9.8 over 2 t squared. So let's rewrite this a little, and we'll start with minus 4.9 t squared plus 5.18 t plus 6 equals 0. Alright, so this equation is a quadratic, right? This is the A, right? This is the B, and this is C. So we should be able to use our quadratic formula to solve it. Alright, so let's just have some notes here. A is equal to minus 4.9, B is equal to 5.18, and C is equal to 6. So you probably recall that the solution is what the t is 1 over 2a, then parentheses minus b plus minus square root of b squared minus 4ac, right? So if you carry out the calculations and you'll find out solve, right? Solve, you find out t has 2 roots because it's quadratic, and one of them is minus 0.698, and the other is positive 1.75, both in seconds. Because we're expecting the landing to happen after the launching, we're expecting a positive time when the ball lands. So we'll discard this negative quantity, and we'll have the positive quantity remaining. So this is the t, and that's from equation 2. So if I take this t and I plug it into equation 1, this line here, right? Let's just keep going. Okay. So if I plug it back in equation 1, I can find the horizontal distance. So let's do that. So horizontal distance from equation 1, x is equal to 19.3 times 1.75. And that gets us 33.9 meters. So this is the final answer. I'll put the unit in. Alright, so the next one is equation 3. So equation 3 here, that's this one here, final y velocity. Okay, we don't really know that. So let's also have that added in here. Vy is equal to an unknown. So Vy is equal to initial y velocity was calculated to be 5.18, so 5.18, and then minus 9.8, t is 1.75, right? So this t also gets plugged into this equation. So we have final velocity, which is supposed to be negative, right? It's coming down, is minus 12.0 meters per second. So that's only final y velocity. And we were asked, okay, the time of flight, we actually solve it first, the t, and the magnitude and angle of the ball's final speed, not just the vertical component. So we need to combine this vertical component with the horizontal component. So here it is. Let me draw this. So this is the vertical component Vy, and this is final velocity v. And it is a vector sum of the Vx final velocity, right, with Vy. Because the x velocity does not change, the Vx is the same as V initial x. Right, magnitude or as vector, they're both equal. So what we can do is we can combine Vx and Vy in the right angle triangle with Pythagorean theorem. So let's move down a little bit. We should have enough space. So V should be equal to Vx squared plus vy squared, which is the same as v initial x squared plus vy squared. So vx squared is v initial x squared, which is 19.3 squared. Vy is negative 12, but I never ever square negatives. That's a recipe for mistakes. What if you put your negative sign in the wrong spot in your calculator? Then you'll make a mistake, right? So now square them, square root, and this one gets you 22.8 meters per second. You can pause and just do this yourself. Make sure this value has to be bigger than either one of these two values. So if you find a value that's smaller than either one of these, chances are you put the negative sign in the wrong spot. And I advise you to never ever square a negative. It is unwise to do it. So now we have this. We also want to find the angle. So here, back over here, the angle it makes. We have a y velocity versus x velocity, which is the tangent of the angle. So the angle should be an arctangent of vy over vx. And so the angle, the final velocity's angle is tangent minus 1 vy over vx. So same as tangent minus 1 vy over v initial x, because initial velocity x is also the final velocity x. So now we actually need this negative, right, because it's not squared. So here the x initial velocity is 19.3. Okay, so if you punch this in your calculator, and assuming that you're using angle in degrees, minus 31.9 degrees. So if these two numerical quantities are the same, then you get 45-degree angle. But if the top is less than the bottom, then you get less than 45-degree angle. Also, the negative will be negative, right? So this is the final answer. So as a review, what we did was throwing a ball right from here, and it goes up, comes back down, hit the ground. And what we started first was we had a list of parameters. So we had positions, x, positions y, velocity, initials x and y, and they are calculated from the initial total velocity and its launch angle. And what we don't know, besides this final position x, is also the time of flight and the final y velocity. And the equations we had were these three equations that are from any introductory physics textbook. And then you plug in the values, you start evaluating each equation, and the first equation has two unknowns, x and t, so you leave that here. And then you go to the second equation, you realize the second equation is a quadratic equation. Make sure you understand which one is the a parameter, which is the square the square coefficient, right? So then you do your quadratic formula, you get two roots, you get the one that makes sense, the positive one. And then you can take it back into equation 1, and please do not erase anything here and try to substitute that t, right? Please start a new line. That's well, you have a video of me doing this, but I don't have a video of you doing any of the problems. So if this was erased and replaced by a number, I'll have no way to rewind and see how you got the number, right? I'll get confused half the way. So don't make me confused. You would rather do this and start a new line. And now you have the information, you plug in this value, you get the final x horizontal position, and then you go to the third equation, and you find the final y velocity, and with a right angle triangle, you combine the components together to get the total speed, and then you use arctangent to get the angle, which is a negative quantity. Thanks.